introduce John Barrett, that will give a talk on the Euclidean contour notation in quantum.
Thank you very much. Very nice to be here. And welcome everybody to the physics part of this week. So I'm revisiting an old topic in quantum gravity, and for non-commutative reasons. So there's some motivation in non-commutative geometry for what I'm saying, but actually I'm not going to say very much, if anything, about non-commutative geometry.
It's a bit low the volume. Let me put it this way.
Okay, is that better? Right.
Let's see.
Okay, good. So the first thing I'm going to talk about is gravity, which is sort of the hard bit. And the second part is about fermions. Which I probably won't have enough time to do justice to, but I'll say something about it. And it's a curious subject. It's a combination of things that sort of been well known for decades, but I'm sort of saying it differently, and the overall net result is sort of different. So you'll probably recognize all sorts of equations and formulas from other places. It's very hard to write a new formula in this subject. Anyway, so I want to explain what I want to do right away. So we've got a manifold M. And it's going to be fixed. And I'm not going to say much about it. I mean, assume it's as simple as possible. It's compact, doesn't have a boundary. And I'm not going to ignore its topology and just work in a coordinate chart. So it's not terribly important. So what I'm interested in is curly L, the space of Lorentzian geometries on M. So in actual fact, these are allowed to be a little bit singular. So the fact that the manifold is compact doesn't mean that the geometry is. And curly F, if I can draw a curly F, is the matter fields. On M. And I want corresponding things for a Euclidean geometry. So am I going to have space here? So curly E is the space of Euclidean geometries. On M, and curly F with subscript E is the Euclidean matter fields. And what I want to prove is a formula. Yeah, let's rub a bit out. Geometries. I want to prove a formula something like this, that a functional integral for Lorentzian geometries and matter fields is equal to a Euclidean formula. So the notation is that gamma is a geometry. So gamma is in that space, the field is in that space, and the corresponding Euclidean things are here. So throughout, Lorentzian things don't get any subscripts, but all the Euclidean things get a sub E on them, like this. So that's the scheme. Okay, so so this is a partition function, this is a partition function. I want them to be equal. Just a few remarks. In non-commutative geometry, we have a good definition of this. So this is why I'm interested in it. In fact, we talk about the random spectral triples. So random spectral triples. And in the good cases, you can make these spaces here finite dimensional vector spaces. And then this is just ordinary integration. And if you have the right sort of action here, it's a convergent integral. In fact, we do this, and we've done this on the computer, and we have sort of various results about how this behaves, these geometries here. Okay, so the random spectral triples are based on the Dirac operator as primary variable. So that's one of the reasons I want to talk about fermions a bit later if I get a chance. We don't really know what this is in spectral triple land. So sort of Lorentzian spectral triples is, well, there is some sort of formalism for those, but nobody's ever written down a partition function. And certainly there isn't a proof that any two things like this are equal. So that's sort of wishful thinking at the moment, mostly. There's a little bit of formalism of what a Lorentzian spectral triple is, but that's all we have. In quantum gravity, we have the opposite situation, where people sort of think they know what this means, at least heuristically, because it's a functional integral and we can't quite do that. And there's a big problem in defining Euclidean quantum gravity. Goes back to the work of Hawking and collaborators from the late 70s onwards. And you know, I was in Cambridge for a while. I was actually in Stephen's group, and I always thought that some sort of formula like this was the motivation for Stephen's work on Euclidean quantum gravity. But if you look through the old papers, and I've done that recently, there's never any such formula written. And there is a good reason for it, which is that there's a problem in formulating this for quantum gravity, in Euclidean quantum gravity, and I'll come to that in a minute. Okay. Yes, and also, apart from the random spectral triples, we have the Kohn-Shamsuddin spectral action, which I forgot to mention. Spectral action. Which gives you a nice Euclidean action for ordinary matter fields on a manifold. But it gives you the normal formulas in some asymptotic limit. It doesn't give you the normal differential geometry formulas directly. It's only asymptotically. So again, we'd like to understand this more. Yep. Okay. So that's all the remarks there. Okay, so let's go straight to the proof of this formula. So proof. So I'm going to treat as finite dimensional integrals, as is sort of fairly standard. In quantum field theory, you sort of treat the functional integral as if it's a finite dimensional integral and keep going until you absolutely have to stop and do something because something's gone badly wrong. But so naive quantum field theory does this. And what we do is we think of the space of Lorentzian geometries as sitting in some complex space. So this is complex Lorentzian geometries. And the idea is that this is a complex space, and it's twice the dimension of this space. So it's sort of complexification, if you like, on M. So you can think of this in a straightforward way as allowing the coefficients to be complex. So complex coefficients. So if you're thinking of a metric tensor, you just allow the entries to be complex numbers. So this is not related, well, it's not directly related to complex manifolds. I mean, that's a more complicated thing. It's just complex geometries. And you know, much like you know, Rn sits in Cn, that's sort of a local picture. And then you find a new contour L prime in C. So you can deform this to this. And that's the sort of proof. The idea is that on the new contour, you should end up with this formula, and the old contour was that formula.
I'm sorry.
Yep.
You said earlier that these are partition functions.
Yeah.
N is not in the boundary?
I'm not worrying about boundaries here, so it can be without boundary.
Sorry?
It can be without a boundary. Yeah. So partition function in a very general sense. Okay, so picture is the sort of like this, that there's the original space is some sort of contour along here, and now I've got the plane here is this complex geometries, and then the new contour is going up here. This is all sitting in there. And what I want to do the proof is to add in, so I think of these as n cycles. And I'm going to put in an n plus 1 cycle here, k. So this is move this out of the way. N plus 1 cycle. So this is these are sitting inside C. C is sort of this complex plane here. Okay, and then you're going to apply Stokes' theorem to show that the bound. So the idea is that, yeah, so that let me say, so this thing here, so e to the is with the geometries here, I'm ignoring the matter fields for the moment. The idea is that that's a holomorphic n form. And then Stokes' theorem is applied with, well, use the fact that this is 0, because the d of it is holomorphic, but there are no holomorphic n plus 1 forms. So you integrate this 0, this on here, and then by Stokes' theorem you get that the boundary is 0, therefore this integral here is equal to that integral there. And that's the proof of this thing here. So obviously implicit in that is that this new contour L prime must be somehow the same thing as epsilon. This is the Euclidean geometries here. And that the action then corresponds. In other words, e to the I s of L for L in L prime is equal to the e to the minus the action of, draw that L like that, of, no, sorry, I've changed notation here, gamma and gamma E here, under this correspondence. So there's this gamma. This is gamma E. Okay, like that. So when I make the two things correspond like this, then this formula turns into that formula, and then that's the proof. I think I've said everything I need to say. Is that fairly clear what I intend the proof to be?
You're basically doing what is called a weak rotation. That in a generic manifold,
I was wondering how
the coordinates.
I was wondering how far I could get before somebody would say Wick rotation. So this is not Wick rotation. This is not Wick rotation. It's related to Wick rotation. In fact, you know, sort of technically, some of the bits that come into this are Wick rotation. So what is Wick rotation? Well, Wick rotation is when you have two particular spacetimes. So supposing I have here a black hole, and then I have up here, I have a Euclidean black hole. And these two can be related. In fact, there's a sort of there's a complex manifold here between them. So you can think of there's a family of, in fact, this will generate you a family of complex geometries, which will have a real slice here as the original black hole, and the real slice here as the Euclidean black hole. And of course, because they both sit together in some complex manifold, you can prove things about one space-time related to the other one by analytic continuation. And of course, they're completely different. I mean, the physics of a black hole is not the physics of a Euclidean black hole. It's different physics. And so things that you measure here are only related to things that you measure here. So for example, you might have some parameters, then you have to analytically continue in those parameters to relate the physics is. So you're not proving that things are equal in Wick rotation. I mean, a similar story with Euclidean field theory and Minkowski field theory. They're not the same. It's a question.
So when you write this function integral, I presume you would have had to do some gauge fixing, particularly the diffeomorphisms.
Yeah, of course. All that stuff, yes.
Would you say that the diffeomorphism should also be complexified?
No.
What I was getting at, really, is that in reality, or at least when I see Wick rotation, it's exactly to prove the Cartesian function identity that you wrote, not to equate two different physical situations.
Yeah, so
One of the issues there is that when you make a change in this complex space, you should do, and there is some examples made by this.
Yes, I know.
At the level of turbines, not at the level of coordinates.
yes,
So
that's
you should change
Yeah.
the geometry, not in the sense of changing the manifold.
exactly.
Changing what you are doing,
The
geometry.
manifold is fixed.
Exactly.
It's completely fixed. Yes.
That was my comment. Yeah.
Yes, thank you, yes. In Wick rotation, the manifold does change, but I'm not doing Wick rotation. That's right. Yes, thank you.
Philosophically, it's similar.
Yeah, it's very similar. And in fact, some of the things you do, sort of technical bits you do to prove this have been called Wick rotation in the past. So it gets a bit confusing. And there's, so the original Wick rotation was like this, but now there's a thing called tangent space Wick rotation. Tangent space Wick rotation, which is a lot more similar to what I'm describing here. And it came out in a paper of Samuel, and I think a paper of yours shortly afterwards. So this is sort of a lemma which helps you prove this identity here, that complex Lorentzian geometries are the same as Euclidean geometries. Okay.
Just to be, to understand, you described the geometry through the metric matrix, is it G mu or through the paper?
I'll come to that, yes. I'm about to get more technical. Yes, Chris.
Yeah, so there's the usual question about what set of geometries you're considering, whether they're smooth, whether they're degenerative. One of the key problems with this is that there are some manifolds which don't admit any smooth Lorentzian metrics, but lots of Euclidean metrics.
Yeah.
So the question is what do you do about those kinds of situations?
Yeah, okay, it's a good question. I'm just about to get more technical. This is sort of the introduction, and I didn't say anything about what the geometries are really, because they could be all sorts of things. It could be the standard differential geometry, or it could be some non-commutative geometry, or it might be some other thing like causal sets or something. Who knows? But now I want to get more specific, and then I might be able to answer some of these questions. Okay, so have I said everything? Well, the first thing to notice is that the Euclidean integral this thing, integral, is defined if, so the action needs a lower bound, which can be negative. That's perfectly possible. And I want it to go to infinity fast enough. So to plus infinity fast enough as this geometry here goes to infinity, as gamma goes to infinity. Okay, and then in that circumstance, this integral is a convergent integral. And that, as I say, that's exactly what happens in our computers when we do non-commutative geometry simulations. Yeah, I'm going to come to the oscillating thing in just a minute. But yes, so I'm thinking that this space is some sort of non-compact space, and so it might have infinite directions, and then you have to make sure that this thing converges by forcing it to get large and positive. So where am I going? Yes, I think I'll go up here. So let's be more precise now, a bit more precise anyway. And I want to talk about the conventional situation of differential geometry. So the gravity action, so I'm ignoring the matter for now. 1/16 pi g, which I shall stop writing very soon. So this is the Lorentzian action here. Whoops, omega. So omega is the volume form, which I'm going to assume is positive. So that's the Einstein-Hilbert, that's the cosmological term, and then I'm going to just write plus more terms. And the more terms are important, and they should be important at high energy. So more terms. So what could they be? They could be higher curvature. Or they could be something to do with your formalism intruding into the usual thing, for example, non-commutativity or anything else. Or, and the other thing is, for example, in the Kohn-Chamssadin spectral action, you have a Planck scale cutoff. Okay, so all of that will modify what basically the sort of the high energy behavior of this thing. But the low energy behavior is controlled by this, and that's fairly stable. We think we understand that. Except to say, of course, the constants in front of these things here, this G and lambda, of course, get renormalized by the effects of matter fields. So they're not, these are the bare parameters, not necessarily the renormalized ones. I'm going to insist on the positive cosmological constant. Of course, that is the bare cosmological constant. Okay, so that's the Lorentzian action. The Euclidean action, according to Hawking, is a very similar formula with an important minus sign here. And of course, it's got the Euclidean volume element here and the Euclidean curvature scalar. Otherwise, forms the same and a very important minus sign. Okay. So that's what Hawking tells us. And there's a big problem with this in that this is not bounded below. So this property that I wanted for my proof here, this doesn't hold for this. So I'll just explain why. Well, Hawking didn't put any more terms in, but you can add more terms in, and I will insist that you do, in fact. So, yes. Okay, so plus more. Okay. So Gibbons, Hawking, and Perry pointed out the problem with this. That if you rescale your metric, assuming I'm using a metric tensor with a scale factor, and you choose the right scale factor, then you can make this action arbitrarily negative, which means that e to the minus it is arbitrarily large. And in particular, what they showed was that the Euclidean action of g tilde is still writing 16 pi g. Well, the scalar curvature gets rescaled, as you might expect, but then there's another term let's put G. Let's write it like that, and then the volume form. And this is bad because this thing here is positive, and so with the minus sign here, it makes the whole thing as negative as you like, if you choose a rapidly oscillating omega. So rapidly oscillating omega goes to large, goes to SE, unbounded. Below. So my observation is that this is unphysical, in that if you want to make this rapidly oscillating, you've got to make it oscillate as rapidly as you like, and that means oscillating at frequencies beyond the Planck scale. So, so I don't think their objection is really a physical one, unless you insist on this formula for the action being exact at all energy scales, all the way up to infinity. Then, of course, it's a big problem, because I can make this thing oscillate, and who tells you not to? But I think, in the decades since then, we've learned a lot that this is not the exact formula for gravity. This is only the low energy part of it, and that there should be more terms. And these more terms will then have something to say about this formula here. So I'm going to assume that there's either a limit. So assume either a limit on frequencies. And that's exactly the situation in our non-commutative models, because our non-commutative models actually have a finite number of degrees of freedom. And exactly the way it works is that it's sort of like a harmonic expansion, where you only keep a finite number of harmonics. And it means you can't have a very high frequency oscillation of anything. Or perhaps more conventionally, or that these, these, or suppressed by the more terms. So perhaps these highly oscillating fields are in your theory, but then there'll be some, for example, curvature squared terms, which would then be even bigger. So this fact that the Einstein scalar blows up downwards doesn't matter, in a sense, if something else is behaving even more strongly. And don't forget that higher curvature terms will dominate at high energy. That's the point. So this is really the formula that dominates at lower energies. Okay. Oh, sorry. What am I saying? What did I say? Yes, I'm assuming that, so this point is this formula dominates at low energy, but the more terms here will be important at high energies, exactly where this oscillation of Gibbons, Hawking, and Perry becomes a problem. So exactly where they would expect to show that the scalar curvatures become very negative, or the Einstein action, the action due to this scalar curvature has become very negative, that's exactly where the higher curvature terms would be large, and they would dominate anything going on here. So I claim that that is sort of unphysical.
So what would happen if omega had a low frequency that was over a very large volume of space-time? Wouldn't that be a problem?
Yeah. So this is normalized to the volume, which is one of the reasons I said it was a compact manifold. But I'm going to write a sort of a precise formula which it encodes what the bound is, I'm assuming, in a minute. So yes, in principle, it could be a problem for a very large manifold. Okay, so more technical details. So let's go here. So I'm going to use frame fields. And a spin connection. So my Lorentzian geometries, and now I can be precise, now I'm going to write my L's like this. So L is a tuple of vector fields. So 4 of them, quadruple. So it's 4 vector fields. Oh, and I'm going to insist that the determinant they form is positive. So they're a frame which has a given handedness. In fact, greater than or equals 0, I'll allow them to degenerate, that's okay. Okay, so the LAs are vector fields on the manifold. It's not an index, well, it's just indicating 4 of them. Okay, so four vectors at a point form a frame at every point, unless they degenerate, in which case this determinant can be 0. And the volume form is the inverse of this determinant, because these are frames, not coframes. So it's this determinant to -1 times dx0, dx1, dx2, dx3. So that is positive or zero, or positive or infinite, excuse me. Or plus infinity. So when they degenerate, this becomes infinite, but that's fine. I don't care if the action becomes infinite because e to the minus infinite is zero, which is perfectly good. Okay. So what is my space curly C, my complex geometries? So it's the same thing. With complex coefficients. I'm just going to say with complex, I'm just going to write this complex. So, you know, a vector field, you normally expand it in a basis of some sort with real coefficients, when I'm saying you're allowed to have complex coefficients. And what's L prime? My new contour for complex Lorentzian geometries. It's the set of all frames where the 0th gadget is become imaginary. And again, I want this determinant to be non-negative. Yep.
When you say complex Lorentzian geometry, Lorentzian is also saying, where is there information about the signature? Even
yeah. So the right. So the inverse metric is you know, it's like this. It's eta AB LA tensor LB. Okay, so that's an inverse metric, therefore a Lorentzian geometry. Okay, eta is the matrix with ones.
I mean, by a complex redefinition of LA, you can make eta a B, even a delta.
Exactly, that's the whole point. Yes, exactly, that's the point. So on these complex geometries here, then when I substitute in here, then I end up with, and I didn't say, the e's are real.
And prime is on the border of this complex geometry. The frontier. Like in the path, is there a trace of signature inside the path?
Well, all the geometry, so if you stick with the real geometries here, you can make an inverse metric like this, and it's either of Lorentz signature or it's degenerate. It can degenerate in various ways. But that's it. It can't become Riemannian.
The definition of the angle, you can put it there, eta or delta is the same.
Yes, exactly. That's exactly the point. That's how the Euclideanization works. So, so this L prime is isomorphic to the Euclidean geometries, which is just the set of all E's, E0, E1, E2, E3. So that's just a frame for Euclidean geometry, and then of course det of E is naught, same condition here. Greater than naught. So that's the isomorphism we had between that. And I've missed out the spin connection coefficients. You can put them in too, and they do similar things. So I'm going to forget the spin connection coefficients a lot of the time. They're sort of me too fields. You know, they just do the right thing as well. Okay. So now, in my proof, which is rubbed off here of the formula, I need an n+1 cycle. Which I call K. And in this formalism, it's now this set of complex geometries. I'm going to have a phase factor that can vary to go between one and the other. Okay, and then phi is between 0 and pi/2. And as usual, the determinant of everything here is, okay. So you'll notice that when phi is 0 at one end of this cycle, I get the, in fact, I'll get a Lorentzian geometry, and at the other end I will get, so this is in the complex space of complex Lorentzian geometries. So you should think of all these as Lorentzian geometries. So yeah, so I'll say it again. So when I put phi to 0, it's a set of vector fields, which actually you can reinterpret as a real Lorentzian geometry here. And when phi is pi/2, this becomes I, and then it's one of these complex Lorentzian geometries, which you can reinterpret as a real Euclidean geometry. Yeah, that's the yoga. And you can think of this map between phi equals 0 and phi equals pi/2. You can think of that as sort of Wick rotation, if you like. It's sort of, yeah, the Wick map. And that's what appears in some other papers. Okay. And the next thing I want to do is to make it compact. So I want a compact cycle. So what I'm going to do is remove a sort of scaling factor. So I'm going to write these vector fields here, these real vector fields, as a scaling factor times some standard ones, f, and such that the volume of the f's is 1. And then my compact version of this cycle here, I call K bar, is just restricting the ranges of R. So I have the phase rotation here of R F0, R F1, R F2, R F3. So now phi is in 0 pi/2, and R is in some interval, AB. So if I can draw a picture for this cycle here, I can just get it on, I think. It looks like this. It's like my earlier diagram, but with bits missing. So perhaps I'll make that a bit bigger. So my L bar is down here. So that's when theta is 0. So theta equals pi/2 is here. And this is my L prime bar. K bar is this cycle in the middle here. And then I've got two boundaries here. I've got, R equals A and R equals B. Okay. Right, so let's move that up. Okay, So now I come to the key assumption, which may answer some of the questions. Let's go here. How am I doing for time? Am I right? Another 15 minutes or so? Okay, so it sounds like the fermions are in the bin. So key assumption. There is a universal bound so the Euclidean Einstein-Hilbert action for these Fs so remember this is the frame field normalized to volume 1 is less than or equal to C. So that's the thing that stops the Gibbons-Hawking-Perry oscillations getting out of hand. So this is all taking place on a manifold of size 1. Of course, I can scale everything trivially to any other size you like. And then the bound here scales, of course, with it. Okay. And what you can prove as a nice little lemma is that that's equivalent to this action being, yes, being greater than or equal to some bound B for all E. Of course, well, putting the scaling factor back in. So you can flip between the two. So if you like, this uncovers what this bound here means. It's particularly this bound on this Einstein-Hilbert action here. Okay. So as I say, this so the way I like to think of it is this restricts what's allowed in the Lorentzian geometries. So you can think of it as a restriction of geometries in L, or the geometries that don't satisfy that bound are suppressed by the other terms, or suppression by the more terms. But either way, it comes to the same thing. If the action of due to the more terms of a geometry that violates this bound is very large and positive, then it will give it a very low probability in the Euclidean integral, so it may as well not be there, right? So that's the 2 points of view are sort of the same. Okay, so let's investigate the scaling. Yeah. For all geometries, yeah. So the first statement was about these ones of volume 1, which you can rewrite for any EA by putting on the other side the square root of the volume or something. You could easily. I just prefer it that way, it sort of looks simpler. Okay. So scaling. So these two terms in the action scale very simply. So recall the Euclidean action. you can just pull out the scaling factors, and it's like this. That scales like r minus 2. It's a dimension 2 operator. And this thing here scales like r minus 4. So in particular, you can see that and this is bounded. This is this thing here we've said is greater than or equal to minus c. C minus c. Yeah, this is greater than or equal to minus c r minus 2. That's that minus sign. So you can see that this thing here is dominated by this term when r is small. So I insist on that lambda is positive. And then the Euclidean action is positive for sufficient or non-negative for small enough r. So that's important. Okay, so I'm ready to do my calculation, which is the only complicated thing. Let's get rid of all this stuff. So the Lorentzian action, I want to do a computation. And I want to look at the Lorentzian action along this curve here. I mean, ultimately, I'm trying to prove something like Jordan's lemma or the estimation lemma to show that this integral here doesn't cause a problem. So let's do it. So I'll start with the Lorentzian action. Remember, this is a diagram in complex Lorentzian geometry, so I should use the Lorentzian action. And then the scalar curvature I can split into 2 bits. It's the minus the Ricci of E naught, L naught, okay, so I'm relying on the formula I just erased for the inverse metric. So this is plus the other 3 terms, Ricci of Li minus 2 lambda, and then all times the volume form, the Lorentzian volume form. Okay, and now I'm going to put in my cycle K on K. So this becomes these are shifted by the phase that goes between here, this phase that goes between 0 and pi by 2. So there's twice. This term here doesn't change because these vectors here don't stay real in the cycle K. So I'm just going to call this RS, sort of the space-like parts of the Ricci scalar. And then minus 2 lambda. Then the volume form has a e to the minus I phi times the Euclidean one. And this is very important, and this combines with these phase factors here. This is the action. So I'm just going to rewrite this. well, no. Now I want to compute the imaginary part. I only care about the imaginary part of the action. The real part of the action will just contribute a phase factor, which doesn't matter. So the imaginary part is minus I sine phi so that's this thing here plus RS minus 2 lambda omega E. You see what's happened, because this is e to the minus I phi, that minus sign there has contributed to that minus there, but this, for this term, it's come from here. But the point is that this thing here is the Euclidean action. That's the key calculation. This, in fact, is minus the Euclidean action. So what you get is that as r goes to 0, so as I argued earlier, the Euclidean action is positive because of the cosmological term, and therefore this whole thing becomes 2 minuses I sine phi SE, and e to the I times it is e to the minus sine phi SE. So the point is that this is less than 1. That's the key thing. So in my integration round on the contour here, the whole thing would go wrong if this has the opposite sign, because then I had e to the plus here, and then of course this would be a large contribution. But because it's less than 1, this is a small contribution. As the contour gets smaller, it shrinks to 0. So, that's basically the calculation. You can also look at what happens at r equals b, and that's, there's nothing to calculate from this point of view, because recall that the scaling, wherever it is here, when this is going to be very large, if I take that to infinity, these two terms here will become very small. So they're utterly unimportant compared to any other terms. As long as you have the more terms, these terms won't matter. So the analysis of what happens here is entirely quantum gravity dependent. Depends on the details of whatever extras you put in your theory apart from the Hawking terms. Okay. So that is that. That's the gravity. Well, the other half of my talk is about fermions, which clearly I can't say very much about, but let me say something about it. We're very much interested in fermions because, in the spectral triple point of view, so perhaps I can just sort of summarize what happens. Board. Yeah, I don't need this somewhere. Well, years ago, in fact, 2006 to be precise, we sorted out what the exact internal space of the standard model is in non-commutative geometry. And the answer is it's a non-commutative space of KO dimension 6, as anybody that's familiar with this has found out. So what you do is you take the space-time and you tensor it with this internal space of KO dimension 6, and that generates all the fields in your theory. And you can do this both in the Lorentzian space-time and in the Euclidean space-time. And so I did the Lorentzian version, and Alan Kohn did the Euclidean version. And we both got the same internal space. So I did it comparing with physics in a textbook. He did it comparing with Euclidean physics in some Euclidean world in which that's obvious. I don't quite understand that, but somehow he did. And came to the same conclusion about the internal space. And so it always seemed to me that there should then be a proof that these two theories are equal, but that was sort of lacking. And Fedele and collaborators wrote a paper about this not that long ago, so I thought I'd revisit this. And it turns out that in this framework, you can indeed work out what the fermion theory is on here, and the complex Lorentzian fermion action on here, and then compare it with the Euclidean one, which you would expect either from Alan Kahn's work, if you're doing spectral triples, or if you're not doing spectral triples, from old physics textbooks like Coleman's book in 1960-something. And indeed, the outcome is that the fermion action here is exactly the analytic continuation of the fermion action here. It really is exactly. And the formalism is exactly the same. So that's sort of the message. There'll be large details in the paper when it finally appears. Okay, so I'll stop now.
Comments, questions, comments, please.
As far as I remember, there is a huge degeneracy. I mean, if you fix the curvature, there are a lot of metrics which can give that curvature. In particular, even with zero curvature. I have not worked on it, but I've heard about it. So what happens of these zero modes?
Well, I guess they're still there. Yeah, sure. I mean, I haven't said much about how to compute the functional integral. I mean, it turns out in the non-commutative framework, which I like, it's great because all the symmetries are on compact spaces, so you actually don't need to discard them in any sense. All the diffeomorphisms are unitary automorphisms, and they just generate some compact space of sort of symmetries, and then you can include them or gauge fix them if you like, but it's the same either way. Of course, in a more traditional formalism, you have diffeomorphisms and then you have to gauge fix, otherwise something is infinite, but I guess you still have to do that.
Just a general comment. Very happy to talk about the spectral action, which I think is a good way to see this partition function, and which has, of course, a little bit of its problems with fermions. But actually, this interplay between the spectral action is Euclidean, but the evaluation of Francesco D'Andrea and Max Burkov, I think it's the interplay between the two, and I'm glad that you saw it in terms of my comment about weak rotation. Is I call everything a weak rotation.
Yeah,
your
it's common.
of seeing this is, I think that it tells us about something about the interplay between spectral action, the Euclidean space, and this weak rotation. I think there are still lots of things to be understood, but I think it's a very fruitful way of seeing things, and the spectral approach. I feel guilty because I will not talk about the spectral approach. But
Yeah.
I think that it's a good way to do physics. A lot of people are doing mathematics, but there are these physics things. So
Yeah, so Masood is going to talk about it tomorrow, right?
yeah, Masood is on
Yeah.
But I think it's a very interesting way to do it. Actually, probably you would agree with my Peana about the spectral action.
Yeah,
So since I'm not so familiar with all of this, when I ask how it jumps in, he always tells me, yeah, you have to use this Euclidean theory in order to have this Dirac operator and so on. But you're saying if you start with a Lorentzian structure, you will still get, for instance, the standard model, the same standard model?
yeah,
Some
sure.
unique solution.
Yes, you can still get this Lorentzian standard model, yes.
I see, so it
Yes.
doesn't really matter. It's stuff.
No, from the physics point of view, it doesn't matter. I mean, if you're a mathematician, it matters, because in the Euclidean formalism, the spinor fields form a Hilbert space, but in the Lorentzian formalism, they don't form a Hilbert space. They have an indefinite inner product, which is mathematically awkward, so you don't have the spectral theorem and various things like that. So it would be hard to form a complete axiomatics of what a spectral triple in a Lorentzian manifold is. But I don't care about that. I'm interested in the sort of physics construction and directly how to relate it to quantum field theory. And in quantum field theory, it doesn't care if there's a Hilbert space or not. Yeah, Harold.
But since you mentioned the spectral action point of view, when you start with the spectral action, you will always get the huge cosmological constant. So what do you do?
Well, it's absolutely necessary to get to have a bare cosmological constant of some sort, but that's not the final thing that you measure. It's not the renormalized thing, because that will depend on the matter fields. So it could come out as positive, negative, or zero, as far as I'm aware, by adjusting the matter content.
So you find it.
Yeah.
But I mean, you cannot really fine tune it because in the spectral action you cannot write down the such a gravitational action. It's not here because this is the result. The action that you wrote down here is the result of spectral action, whatever, taking the trace. I mean, you cannot. There is no such bare thing which you can write down on this matrix geometry, which looks like a model. So.
Well, in the Kohn-Shamsuddin thing, there's a free function you put in. The sort of, you write the action as, so the Euclidean action is the trace of some function of the Dirac operator, let's say squared.
You need a scale.
Well, you don't, but I mean, if you want to take the asymptotics, you need a scale, yeah. So to take an asymptotic limit, you put in a constant, not lambda, some different constant, small lambda, and then you take a limit as this goes to infinity, and then you get some asymptotics, which turns out to be formulas like this, using standard heat kernel coefficient stuff. Right, so the cosmological constant in this frame, in the Kohn-Shamsuddin thing, is related to a moment of the function. So it's something like integral of r, f of r, dr, something like that. And since this function is fairly arbitrary, you can then, this can be, and if you don't insist on f being positive, you notice I didn't insist on the action being positive. You can actually make this zero or even negative. But of course, then you put in matter fields and they will induce corrections to the cosmological constant. So what you finally get is can vary.
I don't think so much about fine tuning. Is that here's some, you know the coupling constants now at low energy, like the mass of the Higgs, which is not really a mass term, but mass of something like that. So you know that now the cosmology of constant is basically zero. Yeah. And then this tells you how the flow of the denormalization is going. But fine tuning would mean that you make a tuning of the bare constants to get a quantity.
Could this private conversation be continued in private?
Okay.
Yeah, I mean, this is not necessarily interesting to everybody. Yeah. So, are there further questions? Any to the talk? Okay. Dennis, thank you.